Hello, myself Naveen Kumar Saini. In the course Microprocessor, code KCS 403, today we are going to discuss about the counter and the time delays. So this is the lecture number 4. So first thing is, what is a counter, what is a time delay, and what is the relation between these two points. So counters are used basically for keep track of events like for the for loop. This is an example. So what we need to do, simply first we will give the count to the particular event, and then it will be decrement or increment as per the requirement or the application. And then we have the delay. Delay are used in the setting up reasonable accurate time between the two events. So counting is for the event, and the delay is the time delay between the two events. So these counters and the time delays, it can be implemented by using the software tool, or it can be implemented using the hardware. So here both the implementation software or hardware, it requires the one construct, that is your loop construct. So for implementation of the counter and the delay, then what is the appropriate counter and time delay? So in the case of any of the program, so what we need to do, first we will count the time duration and then count number of iterations, so in which the loop construct will come into the picture. So what is a counter? So counter, a loop counter is a setup by the loading a register by some value or certain values. So because we are talking about the assembly language program in 885, in that loop construct will be occur when we use the n register pair into the for the counting purposes. So when we apply when we give the numbers to the counters, so in that case this counting phenomena will occur by using the two instructions. First one is the DCR, this is the decrement by one the particular register, and the INR, so this is increment by 1 to the particular register value. So these register value can be incremented or the decremented by using these two instructions, DCR and INR. So this is the case when we talk about a single register. When we have the multiple, I mean the pair of register, so in that case we will use the instruction, that is DCX in place of DCR. So this is the DCX. Okay, so this DCX is used for the register pair, and in place of INR use the INX, this is for the register pair. Okay, so this DCX, this particular thing is for the single register, and this is INR also for single register. Okay, so in the two ways we can give the count by using the registers into the counters. So we are very much aware about the 885. If we talk about that, then registers which we have, that is register B, register D, or register L, and register C, E and L. So when we use a single register, then we can use a register B or the register C, register D or register E, register H or register L. So single register can be used for giving the count. So in that case we can use the DCR or the INR. But when we use a register pair, then this is a B C register pair, or we will have the DE register pair, or we can have the HL register pair. In that the DCX and the INX registers are these instructions are used for the increment or decrement. The loop is set up with a conditional jump instruction that loops back or not, depending on whether the count has reached the termination count or not. So second step in that, first we will give the numbers, second we will use the DCR or INR, and third one is we use the conditional jump. Okay, so conditional jump instructions are like the INZ. So by using this INZ instruction, the flags will be affected. Then what is the flow of the operation of the loop count or the loop construct, which can be designed by using the flow chart or described by the using the flow chart. In that, first we initialize the any count value, okay. Then after initialization of the count value into the particular register, then we will come into the loop body of the loop, where we will start for giving the functions in that. Then update the count. So update the count means we are simply using the INR or the DCR or INR, okay. So this is a case when we are using single register. So in that case, we are just simply providing the sum of the number into this register. Suppose we are talking about the register C, and we are giving the register C value FF into the C register. Then we will decrement or increment as per the requirement. Then is there final count? So this is the condition. So this portion is representing the condition. So this condition can be it will be represented as one of the example of jump instruction, that is a JNZ. So if this condition is true, then it will in that, if this final count is reached, then it will come out from there, or if this condition is true, then it will go back to the here. If the count is not complete, then this loop will continue in that case. Suppose this, if this one is not conditional jump, if in place of conditional jump we are using the unconditional jump, so in that case the it will be in the infinite loop, right? But when we are providing the condition, so by using the conditional jump, then we can find the final count, or we can check the final count of the register or the register pair. Then second concept is about the delays. So in that, as we are very much aware that each instruction process through the different steps or the combinations for the instruction fetching, then memory read operation, memory write cycles, and so on. So there are various cycles which is the combination. These are machine cycles which are combinations of the number of T states. Just like the opcode fetch is required the 4 T states, memory read required the 3 T states, memory write operations also require the 3 T states. Okay, so the combination of these, like fetch and memory read, fetch or memory write, or fetch, memory read and write. So by these combinations we can calculate the number of T states, and T state is what? So here I can say that a T state that is equivalent to 1 clock period. Okay, so this is 1 clock period is equal to 1 T state. Then knowing the combinations of cycles, as we said the cycles are fetch, memory read, memory write, then one can be calculate how long such an instruction would require the complete execution process, in which the number of T's, how many T states are there. Then important aspects of calculating time delay is to know about the BMT. So this B is the number of bytes. So any instruction, how much bytes are required for the particular instruction. Then M, that is for number of machine cycle, how many machine cycles are required for that. Then T is the number of T states, right? So T state is 1 clock period, as we said. So to calculate the delay for a given program, so in exam most of the time they ask about what write a program to provide the 1 millisecond of delay or 1 microsecond of delay and so on. So in that case, how we can calculate the delay for the particular program? So for that we have the formula, that is number of T states divided by the frequency, because every microprocessor works on a particular frequency. Okay, so at like 885 work on the 3.5 megahertz of the frequency. Okay, corresponding to the in that range 3 to 5 megahertz frequency is there for the 885. If we have beyond that 86, it will work on the 6 megahertz or up to 10 megahertz for the frequency range. So here the example is mentioned that about for the MVI instruction, move immediate instruction. This is immediate addressing mode. So this instruction requires 7 T states. So this MVI instruction combines the opcode fetch plus memory read. Okay, so these two machine cycles are required to execute the MVI instruction. So opcode fetch required the 4 T states and the memory read required the 3 T states. So when we combine this, then MVI required the 7 T state. Okay, so here it is mentioned that 7 T states are there. So these 7 T states are we can find for this number of T states, 7 T states. Then we have the frequency. As we said, the frequency is for any microprocessor is specific. So for 885, here we are using the 2 megahertz of the frequency. So in that case, the instruction would require 3.5 microsecond to complete. So here this is a very simple calculation, that delay we can calculate number of T states 7 divide by the 2 megahertz. This is a 2 megahertz. So when we calculate that, then this value will be 3.5 microsecond. Okay, so this particular instruction required to execute, and it will take the time of 3.5 microsecond to execute the MVI instruction. So what is the general rule to find out how many T states are required for instructions? As we are aware, in 885 we have one byte instructions, then we have the 2 byte of instructions, and the 3 byte instructions are there. This is a classification of the instructions in 885. The instructions may be the 1 byte instruction, 2 byte instruction, or the 3 byte instruction. So 1 byte instruction require the 4 T state. This is for the opcode fetch. 2 byte instruction will require the minimum of 7 T states. So it may combine the opcode fetch plus memory read or memory write operation. And in that 3 byte instruction, it may require the 10 T states. So when it requires the 10 T states, it means it may be the combination of opcode fetch plus memory read plus memory read or memory write. Okay, so here itself it requires the opcode fetch. It may require the opcode fetch plus memory read or memory write, right? So here this is a combination how it can work, memory read, memory write. Here it can be also memory write as well. So any of the combination is there. So that just for example, we can see that is the 4 plus 3 plus 3. Okay, this is the 10 T states. So here we can see that there is a 4 plus 3. This is the 7 T states, and here this is the 4 T states. So this is the things which we have to keep in mind before solving the delay when we perform the delay calculation into this. Okay, so these things also mentioned in this slide. Opcode fetch 4 T states and read 3 T states. Write operation can be performed by using the 3 T states as well. Okay, so how to calculate the delay? So there are 4 methods in that to finding the delay. First one is very general method by using the NOP or no operation instruction. So this is nothing but the no operation instruction. Okay, no operation, it means it will not affect anything into the program. It will not do anything. But this NOP instruction, because this is one of the instruction which requires that some particular T states. So when it requires the T states, it means it requires the clocks. So it means if it requires the clock, it means it requires the time period. So it means this NOP instruction will require to provide the delay into the program. Okay, so the main usage of NOP instruction is the delay generation, and NOP instruction is taking 4 clock pulses. Okay, so for this case we have to keep in mind it requires the 4 T states for the opcode fetch or the NOP instruction. So here again the fetching, decoding and the executing this particular instruction, because this is the operation of any of the microprocessor, that it will first opcode fetch, then decode and then execute. So just for example, if 886 is required, is working on 6 megahertz clock frequency. So this is the clock frequency of the 885. These are input clock frequency. When we give the when we connect the oscillator of 6 megahertz, then in the internal clock frequency on which the this 885 will work, that is 6 by 2 or divided by 2, that is equal to 3 megahertz. Okay, so this is 6 by 2. So always whenever we use any kind of clock frequency at the input of the microprocessor 885, it will be divided by 2. So this divide by 2 frequency is the effective frequency which on which the 885 microprocessor internally it will work. So from that we can easily determine that each clock period is 1 by 3 of the 1 by 3 microsecond. So NOP instruction will execute in 1 by 3 into 4. Okay, 1 by 2 into 4, that value will give the 1.333 microsecond. So I hope this point is clear to all of you how we are getting this one. So this is the delay, that is equal to number t states, that is 4, divided by the frequency, that is 3 megahertz. So when we calculate this, then this value will be 1.333 microsecond, because this is the mega. So when we take it in the upper side in the numerator, that this value will be 10 to the minus 6, and this is microsecond. Okay, so this NOP instructions is required so that we can find the what is the actual delay, or you can say at what how much time it will take to execute the NOP instruction, that is 1.33 microsecond. So if we use the entire memory with the NOP instructions, so how many what is the memory size which can be accessed by the 885 microprocessor, that is 64 kilobyte. Okay, so in that if we are writing complete 64 kilobyte for the NOP instructions, so in that case the total time delay to execute will be equal to 216 into 1.333 microsecond, and this value will give the 87359 in 0.488 microsecond. So this is this time is not too large, so it means delay will be very less, because this is the microsecond. So this value will be 87 approx 87.39 millisecond. Okay, so in that way this time delay is very small, so we cannot use all the time NOP instructions. So if we require the more time delay, so we have to use another method for increasing the time delay, right? So second method in this series is the delay using the single register, so that is delay loop. So for that one we have one of the that instructions of the program, very small subroutine we can say, that we are using the MVICFF. So what is significance of this MVIC? Because this is an immediate addressing mode, in that FF value will store into the C register. So C register will carry the FF value, this is into the hexadecimal form. Then we are using the loop, because we as we said when we use the counters, so for counting purposes we require the loop construct, and in that first of all we have to give the register with some number. So that number in the hexadecimal, this number is FFH. So we have to convert this FFH, and when it is decrement, so DCRC, when it decrement it will become the FE and so on. Okay, so then J and Z loop. So J and Z, what it signifies? So it signifies a jump if not 0. So what is not 0? So this value is not 0 till it will be executed. So FE, then in that case FD and so on, FA up to the 0. It means it will be decrement from FFH to 00H. So when this loop, when this condition occurs for 00H, then it will come out from this loop. So that is why it is mentioned that this loop will continuously will execute till FF to 00H. Then after that it will come out from that loop. So now So what is the number of T states are required? So just for example, in the previous case we said when we have the 1 byte instruction, it requires the 4 T states, 2 byte instruction 7 T states, and the third 3 byte instructions, it will be required the 10 T states. Okay, so there is some trick into this to finding that. So MVIC FFH, so this instruction is of 2 byte instruction. So this one is 2 byte instruction. So when it is a 2 byte instruction, so it will require the 70 state. DCRC, this is a 1 byte instruction, so it will require the 4T state for the opcode fetch. We have JNZ loop, so JNZ again it is a 3 byte instruction, so it will require the 10 T states. So when we execute this JNZ, so it requires 10 T states and all 7 T state. So this is the very important point which we have to keep in mind. So 10 T states or 7 T states. So if it is executing without the failure of the loop, so in that case it requires completely 10 T states. But at the last cycle of GNZ, when this condition is true, GNZ, if this condition fails, GNZ, if jump is not 0, it means if it is becomes 0, okay, so in that case what will happen, it will come out from that loop. So in the last cycle of this loop will require the 70 states. Just think about that. It is continuously will work f to 0 0. Then when the 0 0 is reached at this location at the register C, when it carries the 0 0 H at the last, so in that case this JNZ will take only the 70 state. It will not take the 10 T states. When it will take the 10 T states, when this loop is continuous, right? When this loop is in continuous till the C is 0 0. So as it becomes the last cycle of C is equal to 0, in that case in the last cycle it requires the 7 T state. I think this point is clear to all of you. So how to calculate the delay? So formula is same. The delay formula, as we are aware, delay that is equal to number of T states divided by the frequency. Okay. So what we required, just in the previous case we have come to know about the MVI. So it requires the 7 T states. So simply what we have done, 7 T state divided by the frequency, it may be the 2 megahertz. So we find it out about a 3.5 microsecond is required. This is only for the MVI instruction. But when we have the loop construct into this program, so in that case we have to find the total T state for this loop particular loop, right? One is the MVI, second is the loop construct. So in that the first instruction initializes the loop counter and it is executed only once, which requires 70 states. So this MVIC, FF, it requires the 70 states only and it will be executed once. The following two instructions, DCRC and GNZ, form a loop that requires a 14 T states. You can see 10 plus 4. The 14 T states are required to execute in one way. If it is a DCRC and then GNZ, simply, then for executing of the one way, it will require the 14 T states. So how many T states are required? Finally, it will be, because C value is FF and this value is 255. So here that will be 14 into 255. Okay. So this is the case when we are considering this is the true conditions, right? But as we said, in the last cycle it will only require 70 states. So in that case what we need to do, we have to subtract the 3. Obviously when previously it was a 10 T states and now at the last cycle it becomes the 70 states. So it means we have to subtract the 3 into this to finding the total T states. Okay, plus 7 T state from this case, MVIC, FFH. Okay, so this is the total T states. 14 into 255 minus 3 plus 7 T states. These are total T states. So what we require now, finally we require the frequency, and if we require the frequency, it may be considered as a 3 or it may be considered as a 3 megahertz, 3 or the 2 megahertz, just for our convenience if it is not given into the exam. Okay, So we can see this calculation. So for that the general formula is given: total time delay, that is equal to T out plus TL. So T delay is the total delay, T out is the delay outside the loop. So this is the case for outside the loop is what? MVI. Then the delay of the loop. So this delay of the loop is for the DCR and JNZ. So in that case the T naught is the sum of all delays outside the loop. If more instructions are written into this like MVIC, FFH, or somewhere is written like NOP here, okay, so it means it will require the plus 4 T states. Okay, so what will happen? It will become the plus 4 T states for the, this is the case for the, if you are using the NOP instruction into that. So this is outside the loop. I hope this point is clear to all of you. Clear? So in that case the TL is calculated as using the formula TL is equal to T total T state into the loop T states into 10. So this 10 and 10 is in decimal form. So it means this FF is in the this is a hexadecimal, but we have to convert it into the decimal form. So this decimal form is 255. Okay, so we can see T out in this case is 70 states, delay of an MVI instruction, then TL, this is for the particular one loop which is given into the question, then this value will be 14 into 255 minus 3. So when we calculate this, then this value will be 3567 T states. Okay, 3567 T states. So you can try this yourself by using the calculator. 14 into 255, then use the minus, just subtract 3 from that, then this value 3567. So here this is the explanation for that which I have just explained, that 14 T states for the two instructions which is repeated 255 times, or the iteration of this these two are the 255 times, and this FF16 that is equal to 255 in the decimal form. So which is reduced by the 3 T states for the final J and Z instruction, and then the total T states which we can be find it out. T delay is equal to 7 plus 3567. This is the outer loop. This is the for the loop, that is into 0.5 microsecond, because we are using the F is equal to 2 megahertz. So it means this number is divided by 2 or multiplied by 0.5 microsecond. Okay, so and the final expression, final value of total delay to execute this program, that is 1.787 millisecond. So most of the in the exam they ask write a program or write a subroutine to find the total delay of 1.787 millisecond. Okay, so we have to calculate this. So what is required? We require the total T states. So total T states, what we required, we have to assume this value as X. So we can assume that. So based on that we can also find the total delay of 1 millisecond by using the number of count. So we have to find the what is the count which will give the this value 1.7 or 1 millisecond. So you can solve yourself in this case. Similar to that, we have the register pair for the counter loop. So as we said, for the register pair we can use the DCX or the INX in the introductory part we said. So in this example, LXI B1000H. So LXI is the 3-byte instruction which requires the 10 T states. DSXB is particularly required the 6 T states. This is a special case of the DCX which requires 6 T states. Move A comma C. So 4 T states are required because this is a 1-byte instruction. ORAB, the XOR, so 4 T states, and the J and Z loop. So this is the loop, but here we are using the ORAB. So this is the OR operation between the A and B. So this is the OR operation between A and B. Okay, so OR operation means this is the plus sign, right? So we have to specify that particularly. So this is the XOR, so we cannot use this. So here it will be the OR operation, A or B. So if this case is both are zeros, okay, so what is the case? In this case, the register A must be same as the register B. When this condition occur, so in that the zero flag will be set. Okay, so when this condition occur, then it will come out from this loop. Okay, so what is the meaning of this? J and Z loop will specify, it will be complete, final count will be there when the zero flag is set. So when this zero flag will set, when we do the OR operation, so when it will be 0, result will be 0, OR operation result will be 0 when both are 0. Okay, this is the only condition. If both are 0, then, so it means we are not going into the program side, we just want to know how to calculate the delay. So how to calculate delay? So outside delay is this one, LXI 10 t states, and this value. So how to calculate? 6 plus 4 plus 4 plus 10, so this value is 24. Okay, so this is the 24 into this value. This is the hexadecimal. So what we need to do? We have to convert into the decimal form. First we have to convert, and then after converting this, minus, what is this? This value is your 10. So we will subtract the 3. Is that clear? So plus 10. So in that plus 10 t states. So this is complete total t states which is required to calculate, right? So calculation is there, 24 into 2496. So this is the decimal value. So this is the decimal value of 1000 to 4096, right? So these are total t states, and then final delay we can calculate by multiplying 0.5 millisecond. So 10 plus 96321 and into 0.5 millisecond. So the answer will be 49.155 millisecond. So I hope you are getting this point. So this is the one of the another example where we are using the FFH. So just try this, how to calculate the final value of this one, 0.524 in seconds. So nested loop, this is nothing but the loop within the loop. So in that case, we have the two loops. First is this loop and second is this one and this one loop. So here how to calculate? Outside loop is this, then inside loop of loop 2, this is a bigger loop. Within the loop we have this one. So first we have to calculate this, and then we can calculate this loop. So I just try this. It is also again very easy. So inner loop will contain the 14 t states, outer loop will contain the 7 t states, 4 t states and the 10 t states. Then apply the same formula. Then delay of inner loop, TO1 outside loop is 7 t states, which is for the MVIC, and TL1 inner loop is, you can see, FF is for the C. So this is the same example which we have just discussed, the first case, single register case. So this value is 14 t states into 255 minus 3. Okay, so this is the jump instruction, so minus 3 we have to do. So this value is 3567 t states. Then 14 t states for the DCRC and JNZ instruction, which is repeated 255. And here this FFH is nothing but, so this is 16 here, and this one is 255 10 here. Okay, minus 3 for the final JNZ. Now T out MVI this, then final is TL1 loop 1 will contain the 14 plus 2574. So this 2574 will come out by adding the 67 plus 7. Okay, so when we use this here, so here we are using the 7 t states for this case. Okay, so 2564 from here plus 7 t states, so we are getting the this one, this number 63574 minus 3. So why this minus 3? This is for the loop JNZ. Okay, so final expression, final t states for finding the total delay 7 plus 574075, and this is the total t states in this program, and delay we can calculate by using the divide by 2 or multiply by 0.5 microsecond, that is 28.706 millisecond. Okay, so I hope this concept is clear to all of you to finding the by using the counter into count values into the register or register pair, and based on that we can increase the delay into the program. Thank you very much.